We are doing a lecture series on a concise introduction to the pure mathematics, and in the previous lecture, lecture 1, we have covered the preface somehow, and then the bit introduction to the states. Now is of the first chapter has two more topics, which are known as proofs and the quantifiers. So let's start with the proofs. Okay, so consider the following mathematical statements. So let's write. First one could be the square of an odd integer is odd. And by an integer, we mean a whole number, one of the numbers. So which numbers? Like -2, -1, 0, 1, 2. These kind of numbers. Number 2 is no real number has a square equal to -1, 3. Every positive integer is equal to the sum of two integer squares, two integer squares, and then integer squares are going to be 0, 1, 4, 9, 16, 25, 36, 49, and so on. Now, each of these statements is either true or false. Probably you have quickly formed an opinion on truth or falsity of each, and regard this as obvious in some sense. Nevertheless, to be totally convincing, you must provide clear logical proofs to justify your opinions. To clarify what constitutes a proof, we need to introduce a little notation. If P and Q are statements, we write. So to write the proofs, we need to define some notations. So let's say if P and Q are statements, we write P, then Q, which says that, to mean that P implies statement Q. Or you can say statement P implies statement Q. For example, For example, x is 2, then x square is less than 6. It is raining, then the sky is cloudy. Other way of saying that, P then Q, or if P then Q. If x is 2, then x square is less than 6. We should write other ways of saying if P, Q, if P. You can also say that the sky is cloudy if it is raining. Okay, right. Now we have something else, which is P only if Q. That is, x is 2 only if x square is less than 6, or it rains only if the sky is cloudy. So these are all the ways to say that. Notice that if P then Q does not mean that also Q then P. So you can say if P then Q does not mean Q then P. For example, x square is less than 6, then it is not said that x is 2. Does not imply. And this symbol is does not imply. However, for some statements P comma Q, it is the case that both P then Q and Q then P. In such a case, we write. So if P then Q and Q then P, in such a case, we write P if and only if Q, and say P if and only if Q. For example, x is 2 if and only if x cube is 8. You are my teacher. You are my student if and only if you I am your teacher. Now, the negation of a statement P is the opposite statement, not P, written as the symbol. Negation statement P is the opposite statement, not P, and denoted by P bar. Notice if P then Q and then also Q bar then P bar. So since if Q bar is true, then P cannot be true. As P then Q. So we can further explicitly show this as, for example, if P is the statement X is 2 and Q the statement X square is less than 6, then P then Q says X is 2, then X square is less than 6, while Q bar then P bar says X square is greater than or equal to 6, then X is not equal to 2. Likewise, for another example, the sky is not cloudy, then it is not raining. Perhaps favoring the obvious, let us now make a list of deductions that can be made from the implication. It is raining, then the sky is cloudy, given various assumptions. So let's make a table. So that as a table, we have assumptions and we have deduction. So it's saying it is raining, means the sky is cloudy. Deduction is that it is not raining. No deduction possible. Unclear statement. Sky is cloudy. Same here. And no deduction possible. Sky is not cloudy. It is not raining. Now, let us put together some examples of proofs. In general, a proof will consist of a series of implications proceedings from given assumptions until a desired conclusion is reached. As we shall see, the logic behind a proof can take several different forms. So let's give us our first example of a proof, which says that suppose we are giving the following three facts. One, I will be admitted to University of Manchester only if I am clever. B, if I am clever, then I do not have to work hard. C, I have to work hard. What can be deduced? Question is, what can be deduced? And the answer will be write G for the statement which statement? The first statement. I will be admitted to University of Manchester. Manchester, and write C for the statement. Which statement? That I am clever, and W for the statement I have to work hard. Then part A says G implies C, and B says and B says C implies W bar, because in B it says I'm clever, then I do not have to work hard. So that is negation of W. W is to work hard. And hence W implies C bar, and C bar implies G bar. So if you are not clever, then you will not be admitted to the University of Manchester. Something like that. Now, since W is true by part C, we deduce that G bar is true. I.e., I will not be admitted to the University of Manchester. Which will be, so you can say G bar is I will not be admitted to University of Manchester. That is a clear way of using these statements and proof. Now let's talk about example 2. Says that the square of an odd integer is odd. The square of an odd integer is odd. Proof. Let n be an odd integer and n is 1 more than an even integer. Then n is 1 more than an even integer. So n is 1 plus 2m for some integer m. Therefore, n square is 1 plus 2m square, which is 1 plus 4m plus 4m square, which is 1 plus 4 into 4m plus m square. This is this is 1 more than 4 into m plus m square, an even number. Hence, n square is odd. That's the proof. Now, formally, we could have written this proof as the following series of implications. Is we could have said n odd than n is 1 plus 2m, which is n square, which is 1 plus 4 into m plus m square, then n square is odd. We could have also said this. However, this is evidently somewhat terse, and such an approach with more complicated proofs quickly lead to unreadable mathematics. So, as in the above proof, we insert words of English to make the proof readable, including words like hence, therefore, than, and so on, to take the place of implication symbols. Yeah. The above proof shows rather more than just the oddness of n square. It shows that the square of an odd number is always one more than a multiple of 4, i.e. is of the form 1 plus 4k for some integer k. There's something more. The proofs given in example 1.1 and 1.2, or like example 1 and 2, would be described as direct proofs, in that they proceed from the given assumption directly to the conclusion via a series of implications. We now discuss two other types of proofs, both very commonly used. The first is proof by contradiction. And to say that, proof by contradiction. Suppose we wish to prove the truth of a statement P. A proof by contradiction would proceed by first assuming that P is false. In other words, assuming P bar, we would try to deduce from this statement Q, so this statement Q, that is probably false. For example, Q could be the statement 0 is not, 0 is 1, and something like that. Having this done, we have shown P bar imply Q. P bar imply Q, hence also Q bar imply P. and we know Q is false, so Q is true, and hence so is P. So we have proved P as desired. So all I have said here is I'm gonna show by the example 3 says that let n be the integer, be an integer such that n square is a multiple of 3, then n is also a multiple of 3. Now, remember, we are proving by contradiction. So the proof will start like this. Suppose n is not a multiple of 3. Okay, then we divide n by 3. Then we divide n by 3. We get a remainder of either 1 or 2. In other words, n is either 1 or 2 more than a multiple of 3. If the remainder is 1, then n is 1 plus 3k for some integer k. So n square is 1 plus 3k square, which is 1 plus 6k plus 9k square, which is 1 plus 3 into 2k plus 2k square. But this means that n square is 1 more than the multiple of 3. That n square is 1 more than the multiple of 3, which is false. Which is false is we are given that n square is multiple of 3. If the remainder is 2, then n is 2 plus 3k for some k, integer k. So n square is 2 plus 3k square, which is 4 plus 12k plus 9k square, which is 1 plus 3 into 1 plus 4k plus 3k square. Which is again false, which is again false, is n square is a multiple of 3. Thus we have shown that thus we have shown that assuming n is not a multiple of 3 leads to a false statement. Hence, as explained above, we have proved that n is a multiple of 3. Hence, n is multiple of 3. Right. Now, in the next part, we will explain more about how these proofs other works, and then we will also talk about the quantifiers. Thank you so much.